some ideas on vectors that we looked at in the last class. So first of all, if we are um, you know, let's keep it general. Let's say we have point one, which is x one, y one, z one, and point two, x two, y two, z two. So here's our point one, and here's our point two. The displacement vector from point one to point two, we write as a vector p1 then p2, from point one to point two. That makes sense. And um, our displacement vector is pointing. So the arrow is pointing from point one to point two, and that displacement vector has um, the following the way that we calculate that is x2 minus x1 plus, and that's in I direction, x, y2 minus y1 in the j direction, which is y, and z2 minus z1 in the k direction, which is z. And when we get that, um, here is our displacement vector. And what is its magnitude? Well, its magnitude is the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. This is just the Pythagorean theorem. I know it looks a little bit different because it's in three dimensions, but it's just the Pythagorean theorem. So that's the component of a displacement vector, and a special displacement vector, very unique one, is the displacement vector that is between a point and the origin. So it's the displacement of a point from the origin. So in other words, we've got some point here and the origin. And the this is just a, a set case of what we looked at here. Two different points. Only now one of our points is the origin. So the difference between x naught and 0 is just x naught in the I direction. And y naught minus 0 is y naught. And z naught minus 0 is z naught. And we write this position vector because it's a a unique special position vector. We write it as r sub 0, and the 0 indicating from the origin. And so what would be the magnitude of this vector? So the magnitude of r sub 0 or r naught, either way you want to pronounce it, r sub 0 or r naught equals square root of x squared plus y squared plus z squared. And they should be sub zeros just to correspond to this point. Okay, so that's a displacement of a point from the origin. Okay, so let's kind of idea is if you have two vectors, uh, vector v plus uh, w, you just add their components. So you add the x or so the I components, and you add the j components and the k components. Um, Similarly, scalar multiplication, you just multiply the scalar to each of their individual components. So let's look at an example of that. Um, let's say that, well, I think we can look in the next page. No. So let's say that V equals 2I plus 3J plus 4K and W equals 5I plus 8J minus K, and vector V plus vector W is the sum of those. So just adding the I components, it is 7I plus 11J plus 3K. And negative 2 W is going to equal, we'll just multiply negative 2 by each of those component values. So it's going to equal negative 10 I minus 16J plus 2K. Okay, um, we mentioned unit vectors in the last in the last video. So again, the unit vector is a vector whose magnitude is 1, and I and j and k are the special vectors because they're unit vectors in the direction of the coordinate axis. They're in the directions of x, y, and z. But you can have a unit vector in any direction. The key for a unit vector is just the I mean the definition is that the magnitude is 1. So the idea is let's you know if you have some vector v, and in this case we're saying the magnitude of v equals 10, then taking the vector v and dividing by its magnitude will get us a unit vector. So this will get us a vector of magnitude equals 1, but it's now in the direction of v. So we've created a unit vector now. And again, unit vector, which means that it has a magnitude of 1, and it's in the direction of v. So we've created this unit vector in the v direction. And let's let's do the same thing for right here. Well, what are the steps? The first thing that we need to do is we need to find the magnitudes. The magnitude of V here equals the square root of their components. So 1 squared plus 3 squared, which is root 10. So our unit vector is going to be V over root 10. And we know that we can distribute that to each of the components. So this is going to be uh, 1 over root 10 I plus 3 over root 10 j. And now we've created a vector that's in the direction of v, but that has a magnitude of 1. Why are we doing this? Well, this is going to be hugely important for us um, coming up in the next couple chapters. Right now, we're just building a skill. This is just a skill base for us to take some vector in any direction and to be able to shrink it down into a unit vector that has a magnitude that equals 1. Okay. Okay. So let's look at an example of a unit vector. Um, that points radially out, radially outward away from the origin. So you've got some. Let's y. Or sorry, z and x and y. So we've got some starting at the origin, and it's pointing out radially. Uh, to X, Y, Z. And the key thing is that it's a unit vector. Okay, so the idea is this: the green vector that we just drew there is going from the origin. It's going from the origin out to the point x, y, z. And we want we want to find a unit vector at that point. So let's try that unit vector. The unit vector is starting from that point and going out. And it's in the same direction. It's in the same direction. It just only has a length of one. So the idea is our our green vector our green vector, let's call that V, equals uh, xi plus yj plus uh, z k. And we want to create a unit vector, unit vector that's in the same direction as V, but that's a unit vector. So U should be V divided by the magnitude of V. Okay, well, what's the magnitude of V? Uh, we know that the magnitude of V, and we looked at this in the last couple slides, the magnitude of v is just the square root of x squared plus y squared plus z squared. So our unit vector equal, sorry, that's plus. Our unit vector equals 1 over the square root of x squared plus y squared plus z squared. And that's my lambda, that's my scalar multiplier. And I'm going to multiply that by v. So x I plus y j plus z k. And so this unit vector now is pointing in the same direction, radially outwards. And that's the important thing. So from the origin to the point is going radially outward from the origin. So that gives us the direction that's radially outward from the origin, and then dividing it by the root x squared plus y squared plus z squared ensures that it's a unit vector having length 1. Okay, let's talk about another important vector, and this is the velocity vector. The velocity vector is talking about um, this the well, the magnitude is the speed of the object, and the direction is the direction of its motion. So let's think about uh, an example here we've got a car that's traveling north at a speed of 100 kilometers per hour. So we could represent that with a vector like that. It's going north if we define north, east, southwest, typical, um, and it's 100. So this length is representing 100. And it says, well, a plane above is flying horizontally southwest at a speed of 500 kilometers per hour. So to represent that, well, if this is our car, the plane, which is above, is flying southwest. So when it says southwest, we're assuming that that's like a 45-degree angle. And what I tried to do here uh, um, is draw this the length of the red, the plane should be 5 times as long as the length of the green, because the magnitude is 5 times as much. So here's the way that we can visually depict those velocities. Let's think more about velocities. So there's a ball moving with some velocity v, um, velocity vector, and, and when it hits the wall at a right angle, it bounces straight back. So imagine here's a ball, and it's traveling with a velocity v, and when it hits the wall, uh, it bounces off, and now it's moving 20%. So what's new velocity in terms of the old one? Well, if it's reduced by 20%, that means it's 80% of the velocity. So 20% is reduced, so 80% is left over. So my new velocity is 0.8. My old velocity, but it's in exactly the opposite direction. So negative 0.8, my old velocity. The negative means that it's going back, it's in the other direction, and the 0.8 is saying that it's been reduced by 20%. Okay, so a couple important rules, uh, some of which we've gone over, uh, others of which we can just kind of explain really quickly. The idea is, um, first of all, commutativity of vectors. It doesn't matter the order in which you add them. It doesn't matter the order in which you associate them, either when you're adding multiple vectors or when you have multiple scalars. So here, u plus v being associated plus w is the same as u plus v plus w associated. Doesn't make a difference. Um, distributivity. So if you have a plus alpha plus beta times v vector v, we can distribute, and these are both times v plus beta times v. Um, and that's distributing two scalars to the vector, or if you have a scalar times two vectors being added, you can distribute that scalar across the vectors and get alpha times vector v plus alpha times vector w. So commuting, associating, distributing. These are topics that we talked about in algebra. You know, slightly different ideas. In algebra, it would be like x plus y equals y plus x, but it's the same idea. Only now we're talking about vectors. And then the last thing to touch on, just some uh, uh, this is more definitions than anything else. These are called identities of vectors. So vector identity. Uh, if you multiply any vector by one, it's just the vector. If you multiply any vector by 0, 0, a vector plus 0 is the vector back, and um, adding a negative vector is the same as subtracting. All right, we're going to do one of the, we're going to do one problem. Stop this video, and then in the next video there'll just be a plethora of example problems. So we've got four variables here represented, uh, and what's going on. So we've got vector I, which is the number of copies made at each of the four centers in December, and J is the same for copy centers during the previous 11 months. So we're talking about a full year here if you add them together. So we're adding I plus J. When we add I plus J, we're talking about the previous 11 months plus December. So what does the sum represent? The sum represents uh, number of copies in the full year. And what is the sum actually? What is the sum to compute it? I think what might be helpful is if we write I right below J, and the important thing to remember is that we're just going to add the components, so the same components. Should be a 4. So I plus J adding down, we get 356, and then here and now we're adding the third entry, and now the last entry. So we have 2 1, carry the 1. So that means 356 copies at the first copy center, 3,268 at the second, 2,195 at the third, and 3,212 at the fourth. And that's telling us the number of copies in the full year. All right, so I'm going to stop this video. In the next video, it's just problems, problems, problems similar to the ones that you'll be looking at during class or during the next assignment, rather.